We're now going to talk briefly about the synthesis of carboxylic acids. If we look, there are several different strategies we can use for making carboxylic acids. We're going to start by talking about oxidative strategies, which are a very common way to make carboxylic acids. So to do an oxidative strategy, we would start with something at a lower oxidation state, for example, a primary alcohol or even an aldehyde, and then we would treat it with an oxidizing agent. So there are actually two different oxidizing agents that are commonly used to do this. The more old-fashioned is warm KNO4 with hydroxide, followed by hydronium. And sort of the newer one is the Jones reagent, which is chromic acid. So you can pair up any of these two starting materials on the left with any of these two reagents. So for example, primary alcohol with Jones, carboxylic acid. Aldehyde with warm KMNO4, carboxylic acid product. We have also seen that we can make carboxylic acids from cutting apart alkenes. We called this the oxidative cleavage reaction. This was a reaction we studied last semester. We started with an alkene, and the important thing was to make a carboxylic acid, the alkene, the carbon-carbon double bond, had to have at least one hydrogen directly attached to the double bond carbons. We treat it with warm KMNO4 and hydroxide, followed by hydronium. There should be a plus sign there. And what we would get is we would cut the double bond, we would insert oxygens on each side, and then any of the hydrogens that were attached directly to the double bond would be oxidized up and replaced with hydroxides. So in this case, you can see on the left, we have two carbon groups, so that would become a ketone, but on the right, we have one hydrogen, so that side would become a carboxylic acid. We also saw earlier this semester that we could oxidize alkyl benzenes that had carbon groups on them. We could oxidize the side chain. The classical way to do this is hot KMNO4 with hydroxide followed by hydronium. We also saw that you could use Jones reagent, and really the only difference between these two was that for Jones reagent you had to have at least one hydrogen on the benzylic position directly attached to the carbon that was attached to the benzene ring, whereas hot KMNO4 would degrade any carbon group down to the carboxylic acid. The next reaction we're going to look at is a new reaction. We can actually do a reduction of carbon dioxide. If you recall from our oxidation reduction table, carbon dioxide is more oxidized than a carboxylic acid. So if we reduce the number of heteroatom bonds to that carbon, that should move its oxidation state down to a lower one. So for example, if we take one bond away and replace it with a carbon group, then we would have a carboxylic acid. To do this, we use a Grignard reagent. So this is written from the point of view of having the Grignard reagent already formed. So here we have R minus, magnesium 2 plus, X minus. So X minus could be chlorine or bromine. We would add carbon dioxide, and then we would add water. And what we would get is the carboxylic acid that was one carbon longer than our starting Grignard reagent carbon group. The mechanism of this is actually reasonably straightforward. It follows directly from the Grignard reaction mechanism that we've already studied. So what we see is that the carbon behaves like a carbon nucleophile, and it's attracted to the central carbon of the carbon dioxide, which has a large partial positive because of the two oxygens directly attached. So it makes a bond. In order to make room for that bond, it has to push a pair of electrons out of the way on one of the carbonyl C double bond O bonds. So we get an intermediate that looks like this. See, we now have a new bond here to the central carbon, and then one of the C double bond O's. The pair of electrons have been moved out, and it now has a negative charge. And then what we have to do to get the carboxylic acid itself is, in a separate step, we put in hydronium to do acid-base reaction and protonate it. The final synthesis that we're going to look at of carboxylic acids is doing a heteroatom exchange reaction. In particular, what we're going to do is we're going to start with a nitrile. A nitrile has a C triple bond N attached to a carbon group. And if we look at the C triple bond N carbon, the nitrile carbon, that carbon has 3 bonds to nitrogen. So that would be equivalent to, in oxidation state, to a carboxylic acid, which would have 3 bonds to oxygen. In order to do this hydrolysis, we're going to put in hydronium, in other words, water plus aqueous acid. And very often you're going to see it written with heat, although it's not necessary to write the heat. In practice, probably we do most of the time heat it up a little bit. What would happen here then is oxygens from the water that's present in the aqueous hydronium would replace the bonds to the nitrogen, and so we would get two oxygens with a total of 3 bonds attached to them instead of the 3 bonds to the nitrogen. This is actually going to follow our typical heteroatom exchange reaction with a PRAM type of mechanism. So if we look at what we need to do, we need to add a water, add a second water, and then remove the nitrogen. So what we're going to do is we're going to start with our nitrile. To add a water, we're going to protonate, add the water, make stable. So these steps would look like this. We protonate the nitrogen. That activates the nitrile carbon for the weak nucleophile. The water, which is a weak nucleophile, will add, and to make room, it will push a pair of electrons out of the way onto the nitrogen. So we get this intermediate. The water has a positive formal charge, and so therefore we're going to want to deprotonate that in order to make it stable. So this is our first intermediate. So our first 3 steps were PAM, protonate, add, make stable. We're then going to do something very similar to add the second water. So we're going to protonate again on the nitrogen. So we get this intermediate. We're going to add the water. It's going to make a bond here. It's going to push a pair of electrons out onto the nitrogen. Now we have this intermediate. And now, again, the water has a positive charge. To make it more stable, we're going to deprotonate it. That's a make stable step. We get this intermediate. Finally then, to remove the nitrogen, we protonate again on the nitrogen to make it a better leaving group. It will now leave very comfortably because it becomes ammonia, which is very stable. And while in theory this last step should be reversible, what we see is that once it leaves, what we get is this intermediate, but this intermediate is stabilized by resonance, where one of the lone pairs on the oxygen moves down toward the incomplete octet on the central carbon, so that this resonance structure is probably the major contributor. And in this resonance structure, we have 2 very acidic hydrogens. And so base is going to deprotonate that to make it stable. But if we look at ammonia, ammonia is a base. And so probably this base would effectively be the ammonia. It would deprotonate and therefore not be available to go backwards. So that would be a protonate, remove, make stable. So what we have here in sum then is PAM, PAM, PERM. Now, nitriles to make carboxylic acids can be very useful because they're relatively easy to make from primary alkyl halides doing an SM2 reaction. So that reaction looks like this. This is an observed reaction that you should probably memorize. We're going to talk about it later this chapter again. So we start with a primary alkyl halide. We put in potassium cyanide, so it's potassium plus, cyanide, C triple bond N minus. And we put in DMSO. We need DMSO to make the potassium cyanide dissolve, but we use DMSO because it is a polar aprotic solvent which favors SN2. And now what will happen is the cyanide will do a nucleophilic attack on the primary carbon. It will push out the halogen leaving group, and there we go. Get our nitrile. We also, in a previous chapter, talked about making cyanohydrins. Cyanohydrins are nitriles. They're a special type of nitrile because they have an adjacent OH, but they are still nitriles, and so therefore we can make carboxylic acids in a two-step procedure starting from a ketone. We first put in the ketone, we put in HCN with catalytic KCN, the C triple bond N adds to the ketone, and we get this cyanide, this nitrile, that has an OH on the second carbon. We can then treat that with aqueous acid and heat to hydrolyze the nitrile, and what we get is this. The nitrile has now become a carboxylic acid. And if we look, what we've done is we've made a carboxylic acid with an OH, with a hydroxyl group on carbon 2. This was actually a very important way of, early on, of synthesizing important biologically active carboxylic acids from scratch.